Hello and welcome to Saturday's edition of Cracking the Cryptic. Oh, I almost forgot what day it was then. I didn't mean to do that. We're going to be having a look at this rather beautiful sort of wormy puzzle called Equal Split Lines by GDC and Sudoku. So that's about 400 IQ points that have gone into creating this puzzle. And it's region sum lines, for those of you who know what that rule set is, but with the twist that rather than 3x3 box borders dividing these blue lines into segments, the funny circles divide the blue lines into segments. So apparently this is wonderful, absolutely wonderful. It's been recommended to us many times and the rule set is very short. So I'm planning to have some fun with this in a moment or two's time. I'll read you the rules then. Now, what can I tell you about before that? I forgot yesterday, didn't I, to do a Patreon update. So we have a competition running over on Patreon at the moment, which is a new Sudoku hunt from Blobz, themed on Nurikabe, which is sort of a Japanese logic puzzle. So lots of Sudokus with Nurikabe and Sudoku rules. And so it was 505 patrons have managed to solve the whole thing as of a couple of days ago, and 1,587 had done even one puzzle. Now let's see where that is now. So what was it, 505? It's gone up by nearly 200. Oh my goodness. And the ratio is closing. So I think this is a testament to any good hunt, is where people start to solve it and then they obviously get hooked and they really make an effort to finish the whole thing. So fantastic work from the nearly 700 of you who've managed to get through all of the puzzles now. You will be in the draw to win the chance to make a Sudoku video with me, which you might not want, in which case you get gaming keys instead. But if you would like to make a Sudoku video with me, you'd be most welcome. And I think we'd have fun. And indeed, I must mention that on Monday morning at 10 AM UK time, we're releasing a video of my solve with Hugo Schneider, the huge American YouTuber, sort of music producer, music maker, chess international master, just general polymath. I really enjoyed meeting Kurt. He's been sort of a what do we call them, parasocial friends, somebody I've been corresponding with since COVID basically, but it's the first time I've actually got to meet him and talk to him and to see his Sudoku solving live, which is quite incredible. So do check that out. I say that's coming at 10 AM UK time on Monday. Now what else did I need to mention? I think there were other things, but I can't remember what they were. So let me do some birthdays and other announcements. I have some of those to do. We'll start off with Amy over there in San Francisco, a city I've been to 2 or 3 times. Absolutely beautiful place. And Amy, it's your birthday, and I owe you thank you because you got your mother hooked on the channel as well. I think your mother's name is Claudia, if I'm not mistaken. So Amy, I hope you have a great birthday today. And I hope you get some chocolate cake. Next, Debbie. Debbie, you have turned 38 today. And I know this because your partner, Rika, wrote to us. I hope I'm saying your name correctly, Rika. And Rika is making sure that you have ample chocolate cake today. So Debbie, I think it's going to be a very special birthday indeed. I look forward to hearing about it. Now, next, let's have a look at, or let's say happy birthday to Christina. Christina, it's your birthday, and I know this because your boyfriend John wrote to us, and said that you love Winnie the Pooh, as do I. So I'm right behind that, and a good cookie cake, and so do I. So Christina, I hope you have a great birthday, filled with AA milk and heavily iced cookie cake. Now, the next one is not a birthday; it's a marriage. Vari and Jason, it's your wedding day today, and I know that Vari has created a sort of wedding-themed Sudoku for the guests to try. That is fantastic. And well, I'm sure your wedding day will go splendidly. If I'm not sure where you are, but if you are in the UK today, we have had amazing weather. So that I hope has blessed your wedding. I'm sure there will be cake. And thank you for watching the channel. And then finally, Steve. Steve, you've turned the big 6-0 today. And I know this because your wife Mandy wrote to us and told us that I think Mandy listens while you actually watch the solves. So Steve, thank you for doing that. And I hope that today is a brilliant birthday. I'm sure it will be. And that is all the news. Let's have a look at equal split lines by GDC and Sudoku. The rules are very short and are as follows. We have got normal Sudoku rules apply, which means we've got to put the digits 1 to 9 once each in every row, every column, and every 3x3 box. Dots divide lines into segments with equal sums. Digits may not repeat within a segment. Okay. E.g. 8, 3, 5, 1, 2, 5. Is that an example that I can find in the puzzle? Actually, I could make that example, I think, from there. So I think what we're being told is this blue line here is divided by the dots into segments. So this is the green segment. We're going to call that the yellow segment, and this is the orange segment. And the example says that we could have 8, 3, 5, yeah, 3 and 5 add to 8, so that makes sense, and 1, 2, 5 here. Oh, okay, and that does make sense. So the reason there's this rule about digits not repeating within a segment is we could have done this green segment differently, couldn't we? We could have done that, but that's not allowed. That would obey the rules of Sudoku, but apparently it doesn't obey the rules of the puzzle, so that's not going to mean we get it right. Now, I did snip. There was an example over on Logic Masters which I snipped so we could have a look at this together. So let's try and understand how it works. So the left-hand line has 6 on it, 3, 2, and 1. So these sort of cells sum to 6. So these should sum to 6 as well, and indeed they do. They are 2 and 4 in the correct solution. And then this zigzaggy line has a 3 in the corner, and then a 2, 1, and then another 3. So that makes sense as well. Okay, so I think I understand the rules. I don't understand how these pretty graphics are created, but I do like the look of them very much. Do have a go. The way to play is to click the link under the video as usual. But now I get to play Let's Get Cracking. So I think I might start with this line then, because those three, given they all have to be different digits, the minimum these could be would be 1, 2, and 3, and that means this cell, which is a single cell segment, is at least a 6, isn't it? Now, hang on, so that's a 3 cell, a 2 cell. Okay, this is actually, that it doesn't look like it for some reason, but that is a 5 cell segment. And given we can't repeat digits on a segment, that is at least going to sum to 15. If we filled it minimally with 1, 2, 3, 4, and 5, it would add up to 15. So these two digits here, which is a 2-cell sum that is at least 15, have to be from 6, 7, 8, and 9. So that feels like it might be relevant. Here we've got, no, here, that's not very useful, I don't think. That feels like it's a disambiguating, what are they called? Equal split lines, because that's a 2 versus a 2. What's this great big thing here? 1, 2, 3, 4, 5. Yeah, this is more interesting. That is a segment, that is a 2-cell segment, and that is a 2-cell segment. So given that we learnt from this line that a 5-cell segment is at least 15, all of those squares have to be at least equal to 6. Because obviously, I mean, hope that's clear, but we can't, if you put 5 into this cell, that would have to be a 10, or at least, in order to get to the value on that segment. So that is how we're learning this. Now this, this is a very delicate 1-cell versus 2-cell segment. So again, I think that's going to have the same properties as that one. That will be there for disambiguation, is what my prediction is. Now we've got sort of a potion container here, haven't we? An ampoule. So that's 2, 3, 2. That's not so good. 1. Oh gosh, actually I found that for some reason this one I was trying to read as a region sum line. I was doing 1, 2, 1. It's not, is it? It's 1 versus 3. Those 3 digits sum to that cell, so that's got to be at least a 6. Because if this is a 1, 2, 3 triple, obviously that's at least 6 into this square. And the only one I haven't looked at is this one, which is a 2, 2, 3. 2 versus 5 again. So these 2 squares are at least 6, 7, 8 and 9. Right, so it's got to be something to do with these high digits, doesn't it? Let me think. Well, the other thing it could be... Actually, there are... Okay, I'm thinking there are different properties of these lines compared to normal region sum lines. For example, that digit, because it can't repeat on its segment, that digit has to be, I mean, it's not very useful, but it has to be in one of those cells, doesn't it? So there is sort of an extra principle with this. This square can't repeat along its segment, so it is in one of those 3 cells. Okay, no, sorry, I don't actually think that is helpful. Or if it is helpful, it's helpful somewhere I haven't found yet. Yeah, sorry, and the other thing I was going to say is that we do have to have some reasonably small digits on those 5 cells. That was a 5-cell segment, wasn't it? This is a 5-cell segment. So I'm going to say... Yeah, I'm going to say that any 5-cell segment has to contain a 1, 2 and a 3, and no digit higher than 7. And the way I'm arriving at that conclusion is, imagine that you didn't have 1, 2 and 3 on this segment here. Well, then the minimum it could be would be a 1, 2 and a 4, 5, 6. And 4, 5, 6 is 15, and 1 and 2 is 3, so that would be an 18 segment. And I can't make these add up to 18. The maximum value would be 17 if they were an 8, 9 pair. Similarly, if we did try and put an 8 into this square, say, the minimum those could be would be 1, 2, 3 and 4. And again, that takes us to 18 overall, which is too big. So there must be a 1, 2 and a 3 here. A 1, 2 and a 3. It's difficult because they keep going in and out of boxes. It's most irritating. All right, let's try a different tack then. Let's try... Yeah, okay, let's try box 8, where we've got at least 21 in those squares. That is 6 different digits. Yeah, that's it. Right, let's have a look at this. So these squares, we can see they're all different. But the slight complicating factor is that these comprise 2 different, or they're part of 2 different line segments. This segment here and this segment here. But we do know that the minimum sum of those digits is 21, because that's the triangular number for 6. If we populate these cells with the minimum we can, which would be 1, 2, 3, 4, 5 and 6, those digits would sum to 21. But in order to achieve a total of 21, I have used a 1 in there, haven't I? And that's interesting, because what that means is that I can't put 1 in both of those squares. Because if I do put 1 in both of those squares, now I'm not allowed to put 1 in the yellows, because I've got a 1 on this segment already, and I've got a 1 on this segment already. And if I can't put 1 in there, then the minimum sum goes up a lot, probably 27, I want to say. 2, 3, 4, 5, 6, and 7, I think, sum to 27. I'm getting that because I know the triangular number for 7 is 28, and I've deducted 1 from it. It's probably right. So yeah, so my thought is these can't be the same low number, so that I think what we're being told here is that these are a 7, 8, 9 triple. That's what I think we're being told, because what we're being told is we can't double 1 these. Now we could make them different numbers with no problem at all, because let's say this was a 1, 2 pair, then whichever one of these is a 1, that can have a 2 on its segment in yellow, and whichever one of these is a 2 can have a 1 on its segment in yellow. So these could be a 1, 2 pair without problem, but the fact is they're still 1 and 2, they're not double 1. So we've got 21 here plus at least 3 more, which is 24. And what I noticed before is that those digits are all different digits, because these two have to be different by the rules of the puzzle, and this one sees both of those, so it has to be different from these. So these are 3 different digits that add up to at least 24, but can't add up to more than 24, because if these have to be different, the most they can be is 7, 8, 9, and they are therefore 24. So we're on 24 here. We are on 1, 2, 1, 2. These yellow cells are 1, 2, 3, 4, 5, and 6. So the rest of these squares are 7, 8, and 9. Let's take purple out, take yellow out. I've now got a 7, 8, 9 triple in column 6. Hang on. Hang on, I'm sure we can do better. I know, I tell you what, I know these are different. That is definitely something we should try and keep track of. Yes. No. Yes. Yes. Where is green in box 8? Now, green can't repeat on its own segment and can't repeat in its column by Sudoku, so that is green, and that's a 1 or a 2. So green is up there. Now purple can't appear on its own segment, so purple is in one of those squares. I can see these digits all have to be quite chunky now, because none of these squares can be 1 or 2 now, because they see both flavours of blackcurrant and lime. So these are at least 3, 4, 5, adding to 12, which means each of these little things add up to at least 12. Nah, I can't see what to do with that. I don't know. Purple and green have to appear on that one. Oh, hang on, this one. Oh, that's gorgeous. Yeah. See this segment here? Let me just give it a colour for a moment. That is one of these 5-cell segments. So it's got 1, 2, and 3 on it. In other words, it's got both our blackcurrant flavour and our lime flavoured digit on it. Where's the lime flavoured digit on it? Well, it's not there by Sudoku, and it's not there by Sudoku, so it is there. It's exactly here, which means it's over there. Okay, and we've also Well, we have got to put the blackcurrant flavoured digit on here as well, and that's now in one of those 3 squares. It can't be here because of Sudoku. Now, I don't know. I think it's more likely, in a way, to be about the high digits. Do I... Now I've got rid of 6 on here. Is that telling me something I didn't know? It still could be. It's still possible for this line here to add up to 15. So even though I got rid of 6, it hasn't really reduced the minimum, because the minimum was always 15, and I can still make 15. Those 2 digits are the same, aren't they? Because that digit is there. I might as well keep track of that. That digit is not that digit. Yeah, these 2 digits are the same as those 2 digits. So that feels... So this can't be... Yeah, I see. Gosh, that's beautiful. Right. This is lovely. I'm just going to highlight these in different colour for a second. Can I get away with blue there? Hopefully I can. Maybe I'll make it red actually. Is that easier to see? I know people get red-green colourblind though, so maybe I'll go for my... I'm not sure. I do like my indigo, but I know some people say that it doesn't. It makes it harder to see the digits at the back. So maybe I'll go with blue. Right, these yellow and blue are those digits. Because this, remember, these 3 are all different. So this one goes there. These 2 go here. Now what I'm seeing there is, whatever this segment sums to, it cannot have a single way of making it up, because let's say this was a 9-8 pair. Then these squares would be 9 and 8. But this digit, which is part of this 9-8 pair, could not be in that pair, because this yellow digit sees both of those squares. That's impossible. So this cannot be 9-8, and for exactly the same reason it can't be 9-7. Let's do that slowly, just so everyone's clear. If this was 9-7, and let's say that's the 7, it doesn't matter what it is, but because 9... no, that can't be 8. It can be 8 from Sudoku, but it can't be 8 because these are on the same segment, so they have to be different. Sorry, I was suddenly thinking, oh, is 8 possible? It's not. So, if we've got 9-7 down here, this is also 9-7. It's the only way to get to 16 with 2 different digits. And this digit, therefore, has to be in one of those, and it can't be. So that doesn't work. And it would be the same if this was 9. It couldn't go there then. So what we're actually being told here is that there have to be 2 ways of making this total, so that this digit cannot appear in here. So this has to be 15. And now this and this are 7 and 8. This is now 9. And because this can't be a 7-8 pair now, it has to be a 6-9 pair. And therefore, oh, this is gorgeous, right? Orange is that digit, isn't it? So that's got to be 6, that's got to be 9, that's an orange 9. That's just really beautiful. It's just beautiful setting. Right, but this is much more powerful than I've given it credit for, because now these segments are that, well, on this line, this is a 1, 2, 3, 4, 5 segment, and on this line, This is a 1, 2, 3, 4, 5 segment. Now I'm slightly, I might have to do it actually. I mean, I think it would be almost silly not to. Now I know this square is not 1 or 2, it sees both flavours. So that's 3, 4 or 5. This is 1, 2, 3, 4 and 5. Those can't be 1 or 2 because the 1 and the 2, the lime and the blackcurrant are in these 3 squares. So these are 3, 4, 5. Oh no, now I've made a boo-boo because I can't put 6 in this box. Oh dear. So what on earth have I just done wrong there? What on earth have I just done wrong there? Have I gone crazy? This... I've mixed up my lines is what I've done. Let's go back because I've just that's a relief actually, because I thought I was going mad. But I did go mad, but only very slightly. Only very slightly. This line here, which is the 15 line, is actually different from this line. And in my brain, I thought they were the same line. They're not. And that's a big relief. In fact, this is really good, because this is going to disambiguate yellow and blue. Because now this 6 is on this line down here. Well, actually, I might still have to be a bit careful. I was going to say, so this line has to be a 16 line, but that might not be true. It could be 17 if it was 6, 5, 1, 2, 3, couldn't it? Right. So, okay, let's look at this cell. Because what we've got here is a 1 and a 2, so these add up to 3, plus this digit is equal to 7 or 8. So this is 4 or 5. Oh dear. I don't know which one it is. Okay. Okay, I might be more stuck than I thought I was. Let's think. How do we do this then? The answer to that is I don't know. Well, hang on. Have I got a problem with my ampoule now? My ampoule has not got... Well, these digits, they're a maximum of 6. Hang on, what's going on here? So I think the ampoule's got pressure. What I'm seeing is that these squares are a minimum of 3, 4, 5 because they see 1, 2. So each of these dominoes is adding up to at least 12. But we're not... These two squares are a maximum of 6, 5. So they have to be from 4, 5 and 6. If one of these was a 3, one of these would have to be a 9 in order to get to the 12 we know that's at least here. So these are from 4, 5 and 6. Now, what on earth are we pairing a 6? Okay, so these squares, do they have to be 7 and 8? Is that the point? If one of these was 5, yeah, we can't have a 5 here because we're partnering a 5 with a maximum of 6. That only gets us to 11. And we can't use 6, so these have to be 7 and 8. Now, so these have to be 1 apart, don't they? Because if that's 8 and that's 7, these are going to be 1 apart to make sure these are the same number. So given they're 1 apart, they must include 5. This digit is not 5. Now, I was right before when I said that this line is 1, 2, 3, 4 and 5. So there is definitely now a 5 in one of those 3 squares. Now, how do we do this then? Oh, it's very strange with all these squiggly lines and trying to keep track of exactly what's going on and what's on which line. Let me think. Or it could even be, see, that digit can't be 9. Maybe this line comes under pressure. It can't have this well, no, actually, on that bit of it, we never really wanted to put that flavour. Okay, so if this was 4, 5, yeah, okay, then this would be 3, 4, 5. But if this is 6, 5, then it's 13 is the total, and this would be, it's always got to have 3 and 4 on it. And then it either has 5 or 6 as the extra digit. And does that matter for this digit then? Unfortunately, no. That could be the purple, couldn't it? So where's the pressure then here? That's going to be the big trick. I've got to work out where the pressure is. Oh, I see. Where's purple in row 6? That's where the pressure is. It's not here because purple is on this segment. And it can't be anywhere else. That is purple. That is not what I was expecting, but that's purple. Now, is that helpful? Oh, yeah. That's got to be. This is now. I thought this was a disambiguating line, this one, that was going to only come into play very late in the puzzle. I'm no longer sure that is true. And that is because this digit is not a high digit at all. It can't be 6, 7, 8, or 9. So it is a maximum of 5. 5, 4. I'm just going to put 5, 4, 3, 2, 1 in. These are different. So this is 3, 4, 5, 6, 7. It's not 3 or 4. I know 3 and 4 are over there. So it's now 5, 6 or 7. So this is not 1 or 2. Oh, it's close, isn't it? It's very close to being interesting. But, oh, it's not 6 actually. So it's, oh, whoopsie. So it's odd. I'd love to, if that's 7, that would be 5. That wouldn't, well. Can that be, oh, it could be 7. If that's 7, if that's 5 and that's 2. Right, so perhaps what we've got to do instead is to think about... Oh, I'm not sure. I don't know. Is it going to be... What are the options for this cell? It's not 1 or 2, and it's not 7, 8 or 9. So it is 3, 4, 5 or 6. But whatever it is, does it have, it has to be, it has to be 6. There we go. Done it. That's very clever. Not of me. Oh no. Oh, so not of me. But the beautiful thing about this square is it sees all of those. And remember that this segment here is 1, 2, 3, 4 and 5. So this square cannot be 3, 4 or 5 and it has to be 6. That's gorgeous. So these are not 6 and this is now 4-5 pair with a 7-8 pair. So we know that the total we're going for, because they have to have the same total. I mean, so we can see it's 12. There's a few ways you can see it's 12. If you add up 9 plus 15, you get 24, and that's 2 dominoes worth. So it's 12, which means this is 3, 4, 5, which means that is 7 now. So this is, so 7 is forced. That has to be 5, and purple has become a 2. There we go. So that means green is a 1. Let's get rid of our 1s from here. There's definitely a 2 in one of these. Are we going to be cooking with gas? Perhaps. Yeah, 7. So that's 7. That's 8. What do we need? Where's... No, that's a bad question. Bad. Naughty Simon. Okay, if that's 4, 5, that is now 3, which means we take 3 out of these. So this is a 2, 4, 5 triple. And these squares... Oh, look, that's a 4. So this is 2, 1, 4, 7. So, okay, so yellow is 8. And 7 is blue. So this is now even. And we don't know, I don't think we know very much about that one. We know that these squares are a 3-8 pair to complete this box. And we may know the order if I think hard enough about it. And what digits do we need to complete box 7? 1, 6, 9. Yeah, that's a naked single. That C's 9 and 6, look. So this is a 1, which is a green digit. Let's make sure we keep track of that. That's no longer green. This is a 6, 9 pair. That's lovely, because now I know where 6 is in box 8. And if I know where 6 is, I now know where the purple digit is, the blackcurrant digit, which is here. So these squares are now known. Oh, I see. And actually, because we've got 9 and 8 on this segment, that is 17. So these should be 3 and 5. Well, not only by Sudoku, but by maths on this segment, and that does seem to be correct. So now I know what these digits are. 1, 4, 8. So that's a 4. It sees 1 and 8 above it. So this is a 1, 8 pair. In this box we've not put in 2, 3 and 9, so this is a naked single. This is a 2, 9 pair, which we know the order of. Let's make sure that's purple. So there's a purple 2 up there. I don't know whether it has to go on there or not. It might have to. It might have to, actually. Do we know what this adds? Oh yeah, we do. We know this needs a 2 on it. Where does the 2 go? I don't know is the answer. But it's definitely in one of those 2 cells, because by Sudoku it can't be on these 3 cells. We know this must have 1, 2 and 3 on it, remember, in order that this doesn't get too large. That's not 6 anymore because of this. 3 is in one of those 3 squares. But, oh no, that doesn't work. Bobbins. Okay, so what that means is... I don't know yet. I think it means something. That's not 4 by Sudoku. What do we need here? 1, 3, 1, 3, 4, 5 up there. I mean, I'm actually going to pencil mark that. There is also a 1 up here, because this can't be 1. So this is 1, 3, 4, 5. But this could be a 1, 2 pair, I think. So I don't necessarily know that the 1 is here, just as I don't necessarily know that the 3 is here. The 3 could be there on this line. Oh, okay, so I don't really know what to do again. Am I going to get stuck? The answer is perhaps. Oh dear. I'm sorry, I can't see what to do. I'm panicking. Let me... What do you think it is? Those two sum to an even number. Ooh. I don't know whether that matters. I'm just trying to think about that. I'm not sure. Sorry, and I didn't explain why I know that. The reason I know that is that those 4 digits are all even. That's a knowledge bomb for you. They are the digits 2, 4, 6 and 8. So these 2 digits, given 2, 4, 6 and 8, are the only even numbers in Sudoku. I don't know what these numbers are, but I know that they're made up of 2 odd numbers, and 2 odd numbers sum to an even number. So I know these 2 have the same parity. They must sum to an even number. Now, if these were both even, they would have to be 4 and 6, because 2 and 8 have gone from the box. And then these would have to add up to 10, and they would have to be 3, 7. Okay, I don't know why that works or doesn't work, but if on the other hand these are both odd, they couldn't involve 1 or 9, could they? So they'd either be, I'm just going to think about that, they'd be from 3, 5 and 7. In fact, that would have to be 5, because it would see 3, 7, 1 and 9. So this would be 3 or 7. So either these would add up to 8 or 12. 8 is impossible, because this wouldn't have a fat value. This is quite interesting. I think I might be overcomplicating things, which is occasionally a fault of mine. But if this is 3, what I'm seeing there is this domino adds up to 8. Well, it can't be 1, 7, it can't be 2, 6, and it can't be 3, 5, because this can be neither. So that wouldn't work. This would have to be 7, and this would have to be 12 now. And again, this couldn't be 5, 7, could it? It couldn't be 4, 8, so it would have to be 3, 9. Now, that's interesting. That would be a very specific order. 9 here, 3 here. Can we see a problem with that? If that's 9, 3, this would be 5, 7. Don't know. Might be fine. Bobbins. Okay, so I don't think I know. Well, so I know this either adds up to 12 or 10. I'm not sure. sorry. Okay, so let's think again. Is there a way? What do we know about this? We know that this is either... Well, we know this adds up to at least 15, don't we? Because it's these squares again. So if this was not 9, it would be 8, 7 in order to get to 15. And that might be fine. I don't know. So this square is never 8, I suppose, is something we can deduce. Because if that's 8, that has to be 6, and that's only 14. So this is definitely an odd digit. And it's either 7, 8 here. Oh, it could be 9, 8 as well. because this could, I think this could add up to 17. I've not really thought about this length of the line. Maybe that is something it's worth giving some consideration to. That's a purple digit. So purple is, okay. Purple is in one of these three squares. Purple can't be there because that segment is adding up to a maximum of 17. And if this was a 9, it would add up to at least 19 if I made these all minimumed. So 9 is in one of those two cells. If that's 9, did we work out that? Oh yeah, if that's 9, that's a 7-8 pair. Is what we worked out, and this would be 1, 2, 3, 4, 5. And there might be a reason that's either forced or not forced. Oh, the other thought, actually, here's a thought. Maybe it's this one. Do I know what that is somehow? Because I'd forgotten that that 3-cell segment is summing to this, isn't it? These two digits, oh, I don't know. I don't think we know. They don't have 1 or 3 in them. So they're at least 2, 4, but that would still allow this to be 6. And there might be a reason that can't be 1, 2, and 3, but it's not immediately obvious what that reason is. And these have to add to at least 15. And green, okay, green is the digit 1. Let's actually put a corner pencil mark there and think about that. 7 is up there, definitely. So 7 and 9 are in these 3 squares. Can that, that can't be 9, or, oh, it could be 7. That's annoying. It can't be 9. That's definitely true. Because these two digits add up to this digit. So if this is 9, this would have to be a double-digit number. It's almost that this is a 7-9 pair, but it may not be quite forced. 6 is definitely in one of those 3 squares. I don't know. Okay, struggling. I'm struggling to see how to do this. How do we think about, how should I think about this properly? If I could, it could be Sudoku. I mean, I'm well aware of that. Oh, can I do that 1-8 pair somehow? Don't think so. Oh, it's intriguing. Or do I know the order of these? Because I know these are dominoes. Like this could be, this is either 4-8 or 5-7. Is there some reason that we could know which way round that would be? I don't know. I don't know that. I don't seem to know very much, do I? Oh dear. Okay. That digit is on that segment. Oh. Hang on, let me think about that for a moment. That's definitely not purple either. Let's just make that a black digit, because there's a 4-5 pair here. So by Sudoku, there is a black digit in one of those. Now, does that matter or not? Might be an interesting question. And it also might not be. How would that work? I worked out, didn't I, that if both of these were even, how did it work? Yeah, if both of these were even, they were a 4-6 pair. So that would be a 4 in that instance. And these would be 3 and 7. I'm not sure. I was going to say I feel like I don't actually know if I think that's going to be the correct answer or not. I'm not going to guess. I'm not going to. That would be 9. And what would that be? 5. So if this is 4, that's 5, which is a slightly strange thing. Does that matter? I don't know. And if this is 5 and 5 is here, then we know it must be accompanied. Well, it must go here for starters, and it must be accompanied by an odd number, because we know the parity of these. And that digit goes there, and I think we worked out it was going to have to be, yes, we worked out it would have to be 7, didn't we? I think maybe this is something I have to record. So either this is 5 here and 7 here, or it's a 4-6 pair, and we don't know. Oh, hang on. So it's either 5-7 or it's 4-6, but we don't know the order. And this is either a 3-7 pair adding up to 10, where the order is... Can that be a 3? I was wondering, what, because 3 has to go on this U-shaped line. But I think if that's a 3, it can still go here. So I think 3-7, we just don't know the order. Or it's 5-7. These add up to 12. They have to be... It can't be 5-7 because this can be neither. It can't be 4-8, so they have to be 3-9. So there's always 3 on here. Ah, maybe that's the point. Wow. I certainly hadn't realised that. But does it matter? Maybe it doesn't matter. No, it does matter a bit. Well, a tiny bit. It does matter a tiny bit. So what I've now concluded is this is either 3-7 or 3-9. There is a 3 on it. So we know there's a 3 on this loopy thing, and it's not in any of those squares. So it is in those squares, and therefore that is not a 3. I mean, it's the most hideously poor deduction, but does seem to be true. So 3 is in one of those squares, and if that is 3, it would have to be there. So that, all I've got from that is that that is not a 3. I mean, that's... feels distinctly underwhelming. Okay. Oh, 9 is over there. Maybe that's relevant. Can we do something with that knowledge? Oh, 9 can't be here. That is definitely out of bounds, because these 3 digits are adding up to that one. So 9 is now in one of these 2 squares. Can that be 9? Well, it would depend, wouldn't it? It depends what these add up to. Or does it, actually? These add up to either 15 or 17. So if this was 9, these can't add up. That wouldn't work with 15. But it might work. Oh, it's very... It would have to be 926. That's the only way it could work. Is that ruled out for some reason? No, I don't think it is. Wow. So the only way this can be 9 is if this is a 2-6 pair. It probably is a 2-6 pair because I've got a 2. The 2 is almost trying to get onto this line. So if this is 9, this is 2-6, this is 9-8. This would have to be something that adds up to 17. Don't know. Interesting, but I'm not sure how to do it. Okay, sorry. So I have to think again. 1, 3. Oh, golly gosh, I don't know. Is it this digit has to find a home in this box, so it is one of those two digits. I mean, that's probably worth recording. That digit there is one of those two, because it can't repeat on its own equal split line, and it can't go there, and it's not equal to these digits, so it is one of those digits, therefore it's going to be up there. But I mean, I think that's fine, isn't it? Okay. Oh, I'm sorry, I don't know. I'm not sure how to do this. Come on. How do we make more progress? Is there some Sudoku somewhere that I've missed a trick on? Very possible. 4. 4 is in that bubble. Or even, yeah, if I knew which way around this went, it would all be helpful. I don't know. Gosh, I'm really stuck. What could it be? Where are you, naughty break-in? Where shall we look? These digits all have to be fairly small. Could it be, where is... Oh yeah, there you go. Where's 3 in this row is a good question that I didn't ask but should have asked, because that's... Oh, that's huge. That's broken the puzzle open. Because I think perhaps... Okay, so the crucial crux... The crux came a while ago when I deduced these had the same parity. And once I did that, I experimented, I think, with 3, 5 as an option here, and realised that didn't work. And at that point, once 3, 5 comes off this domino, 3 in this row has to be here. And once 3 in this row has to be here by Sudoku, because it can't be there because of this 3, that becomes 8. And look what happens to that. It becomes 6. But we know that's a 5-cell segment, so we have to go 6, 9, which is the... Okay, so that's 9. Because 9, don't forget, is our orange digit. So both of those lose their colour. Definitely they are orange. Definitely that's not orange. 6, we never gave 6 a colour, I don't think. So this digit is now 6 or 9. It's one of these. But this has to be 1, 2, 3, 4, 5. That's not 9. I worked out 3 was here, didn't I? So this square is... Oh, this is a 5. But because remember we worked out 3 was on here. Well, the only... Given this is a 1, 2, 3, 4, 5 quintuple, that has to be 5. It's the only thing it can be. So these are from 1, 2, 3 and 4, and they're not 3. So 1, 2, 4 here. Oh, it's close now. We're getting there, I think. Does this make enough of a difference? I'm not sure. It might do. So do we now know whether this is... If this is 6, this has to be 1, 2, 3, and this has to be 2, 4. That would have to be 7. I don't know. That might be fine. Okay, that's 3. So that's 3 and that's 5. And that's 2. 2 is our purple digit. So this is no longer purple. So we've got 2 flavours of 4 and 5. Oh, it's so close to being... Man, maybe that's worth recording. So, what I'm thinking now, I've got to choose a colour for this, and that's a big decision. Actually, I might not need to. I mean, I know 2 is in one of those squares. So I'm not sure. I'm sorry. I'm still uncomfortable. Okay, hang on. If that's 9, that can't be 9. So this is 3, 7. And if this is 3, 7, we are adding up to 10. And that could not accommodate a 5 in there, could it? This must be 4, 6. There we go. So this is 4, 6. This digit is now 4. That's a 5. These squares don't include 4. So this is a 1, 3. That's a 5 at the top. Now, how do we... Let's tidy up our pencil marks. This now is a 2, 4 pair. This is now a 6. This is a 4. These digits are 3, 5, 7. So the only place 5 can go is here. And this column is a 1, 8. It's got 1 and 8 as its top and bottom digit. Now, okay, we are on 15 here, so this can't be a 9 anymore, because we worked out 9 would have to go with 2, 4 or 1, 5, and that's impossible. So this is the 9 in box 4. That's 9, that's 6. Let's get rid of the orange there. Let's get rid of the corner pencil mark. That gets fully oranged. That gets fully oranged. So now, whoa, okay. So 9 is here now. Now that is... So this domino adds up to 9. It's not 1, 8. It's not 3, 6. It's not 4, 5. That's 2, 7. So it is, we know the order. It's 2 there, 7 there. That's the purple digit. That's the blue digit. These are nothings. Except, I suppose, they are 4 and... Oh, they're 4, 8, which we can do, of course. So 8, 4, 4, 2. That gets fully purpled or fully black-curranted. There's a 2 in one of those. It would be very nice if we knew it was this one. I mean, there are 3 ways of making digits add up to 9 with 3 different digits in Sudoku. 1, 2, 6, 1, 3, 5, 2, 3, 4. I don't know off the top of my head if any of those are ruled out. They may be. But let's think a bit more. Right, this row, what have we not put in? 1 and 6. Right, I bet we might be able to get rid of 6 from this. 6, yeah, that doesn't work. If that's 6, this would have to be a 1, 2 pair. And that would have to be the 2, and this would have to be a 1, and it would clash. So this is 1, this is 6. 1 is the green digit. 6 is, I don't think, ever was awarded a colour. So 1s are in these positions. Now this can't be 2 because that would be 6 and that would clash. So the 2 goes here. So this is 1, 3, 5 and we know the order. 5, 3, 4, 8 because we know that added up to 12. 5, 7. Okay, so what do these add up to now? And the answer is 9 and they are 2, 7. They can't be 3, 6, 4, 5 or 1, 8. So they're 2, 7. That's 8. Okay, this is 3. Here we go. Here we go. We're getting there. Slow. It's been slowly but surely, hasn't it, today? That's a 4. That's a 1. 1, 3. 7, 3, 7. Right, what do we need over here? 6, 7, 8. Yeah. 8, 7, 6. 1, 1, 8. And we need 3, 6, 8. Okay, so I'm going to do that last. That's 3 in the corner. That's 3 in the spotlight, losing its religion. Very, very. I want to actually think about this. So let me just deal with the colouring of the puzzle, because I want to think about. Let's just make all of those. So have we got 9? We've got 9 oranges. We must have 9 blues. I just did the blues. Have I got all the 1s, all the 2s? I think so. Now, okay, so how should I have done that? So, it was a very, very pretty, by the way. I loved the fact I could deduce that those had to be different from this pairing, therefore they had to be 15. That was gorgeous. I then made a mess up because I didn't understand how the lines worked. Then I worked a bit on this, didn't I? And I got this narrowed down. What would have been the correct way to think about it so that I wouldn't have got so stuck? I saw that there was a parity. Yeah, I mean, it's basically just Sudoku. If I spotted the parity point, didn't make use of the 3 until much later. Once I got that 3, that gave me an 8 here. That gave me the 15 total here. Yeah, that gave me a 9 here, didn't it? Once I got that 9, that was a 9. Yeah, and that knocked out the possibility here of the 3-9 pair, adding up to 12, which was necessary if this was an odd pair. Yeah, so I think all of my, not all, but a significant portion of my slowness was not realizing the full implications of this beautiful little line here. And it is beautiful. It's a lovely point. That parity point is beautiful. But what I should have done is rather than keep focusing up here, realize there was an implication in this row. And I didn't. Anyway, is it correct? It must be correct. Beautiful. Very clever. Got me. Well done. GDC and Sudoku. Really, really enjoyed it. I think actually that rule set has legs as well. It's a sort of new twist on region sum lines. Very pretty. Very pretty. Loved it. Let me know in the comments how you got on. I enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.